An ignition gateway running in a Podman container on the iE650 PLC can act as an MQTT client by using Cirrus Link's MQTT transmission and engine modules. These modules enable the gateway to publish data to an MQTT broker and to consume messages. The MQTT modules can be downloaded from Inductive Automation's Downloads website. From the main Downloads page, select Other Operating Systems and Versions, and then navigate to Strategic Partner Modules. Then select the Ignition version deployed. While Ignition modules usually provide some degree of backward compatibility within the same minor version branch, it is recommended to always use the most compatible module version available for the specific Ignition Gateway version in use. Once the mod files have been downloaded, open the Ignition Gateway web interface. From the Config tab, navigate to the Modules section. At the bottom of the page, select Install or upgrade a module. Browse to the downloaded module file. Then accept the license agreement to complete the installation. Repeat the same process to install the second module. After installation, both modules should appear as running under the Cirrus Link Solutions LLC section. In some Ignition versions, such as 8.3, the gateway may require a restart to complete module activation. If prompted, make sure there are no unsaved changes in the designer to avoid losing work, then click Restart and wait for the gateway to come back online. Once the modules are running, new tag providers are created on the gateway. MQTT Transmission Tag Provider exposes both informational tags and writable control tags related to data publication. The MQTT Engine Tag Provider includes similar folders, along with a message diagnostics folder. Additionally, when MQTT Engine subscribes to topics, it dynamically creates folder structures and tags based on the message payload. For this reason, the way data is published must be defined by design. In this example, the data originates from an application running in the CodeSys runtime of the iE650 PLC, which publishes process variables to the local MQTT broker. The application publishes the data as a JSON payload, where top-level such as compressor represent CodeSys structs, each containing their corresponding properties. Now let's configure MQTT Engine to subscribe to topics from the broker. From the Ignition Gateway Config section, open MQTT Engine Settings. As we are using MQTT Vanilla, navigate to Namespaces tab and select Custom, then click Create New Custom Namespace. Give it a descriptive name and, in the subscription field, enter the topic you want to subscribe to. For this example, we're subscribing to all topics under Enterprise, Site, Area, Line 1. The hash symbol acts as a wildcard to capture all subtopics. Enable JSON payload parsing by checking the JSON payload field. This instructs the module to parse incoming MQTT messages as JSON and automatically create tag structures based on the payload content. If the subscribed tags need to be writable from Ignition, enable the Writable Tags option in the advanced settings. Save the configuration and verify that the custom namespace is created successfully. Next, configure the broker connection. Navigate to the Servers tab and create a new MQTT server setting. Choose a recognizable name for the connection and fill in the broker URL according to your deployment. In this example, we are hosting both the Ignition Gateway and the broker in the iE650 PLC, so the same IP address is used along with the default MQTT port 1883. For the server set, the default configuration is sufficient, as only a single broker connection is used. Additional server sets can be created when multiple broker connections are required. These settings are enough to establish the server connection. All remaining options are left at their default values, and legacy state remains unchecked to demonstrate a basic MQTT connection. From the Ignition Designer, the result can now be verified. Under the MQTT Engine Tag Provider, a folder structure is created following the configured topic subscription. The JSON payload is parsed, with top-level keys mapped to folders and their properties created as individual tags. At this point, the iE650 PLC is hosting the MQTT broker and executing the control application that publishes the data, while Ignition acts as a local SCADA and IoT platform. In architectures where data must also be consumed by external systems, the MQTT transmission module allows Ignition to publish it outward using MQTT. The MQTT transmission module provides two types of transmitters. In this demonstration, both configurations are shown for reference, although only one is typically required in a real deployment. To configure the default transmitter, navigate to the Transmitters tab and create a new transmitter configuration. Assign a name and select the tag provider containing the data to be published. In the tag path field, specify the root folder to publish. In this example, the enterprise folder created by MQTT engine is used. Leaving this field empty publishes the entire tag provider. Next, select the server connection. The same server configuration used for the MQTT engine section is reused here. As you can see, now the tags are being published to the SPBV 1.0 root topic according to the Sparkplug B specification, including node and device information topics, and protobuf encoded payloads. If a JSON-based payload is required instead, the data format type can be changed in the advanced server settings to publish the data using JSON. The second option provided by this module is the UNS transmitter. While the main settings are similar, this transmitter publishes each tag and its properties to separate topics, allowing more granular control over what is published. This option is enabled here to demonstrate its behavior. At this point, the server overview shows 2 out of 2 connections succeeded and the UNS transmitter is publishing data under the UNSAV 1.0 root topic. As shown, the UNS transmitter publishes each tag value to its own topic, with the corresponding properties published to separate topics. At this point, both the standard Sparkplug B transmitter and the UNS transmitter have been configured to publish data. As explicitly recommended by Cirrus Link, the choice between them depends on the intended architecture. Sparkplug B is suited for traditional device-centric integrations, while the UNS transmitter should be used when implementing a unified namespace, where data is modeled by business context rather than by source. To close this demonstration, we will now look at the data flow in action, using a reference architecture. In this setup, all components run on the IE650 PLC. Data is generated by a CodeSys application and published to a broker running in a Podman container. That data is then consumed by an Ignition project, which can optionally publish data back to the broker or forwarded to external systems. An application running on the CodeSys runtime of the IE650 PLC simulates data collection from a process plant, specifically variables related to a compressor and its cooling system. These variables are published using the MQTT library included in CodeSys IIoT Library's SL software package and sent to the local broker hosted on the same device. On the Ignition side, MQTT engine subscribes to these messages and converts them into structured tags, which can then be used like any other Ignition tag. A clear parallel can be observed between the JSON payload structure seen in MQTT Explorer and the tags created in Ignition. These tags are bound to a simple perspective view, representing the process. As shown in the video, when values change in CodeSys, the corresponding tags in Ignition automatically update. Although network conditions and processing time contribute to the overall latency, the refresh rate depends primarily on the publishing period. In this case, the publish block is configured to trigger every 200 milliseconds. On the transmission side, we can see how data is sent back to the broker by both configured transmitters. This data could be sent back to CodeSys and used by another custom program to write back to source variables. However, this functionality must be explicitly designed and implemented, as the MQTT protocol does not provide direct variable-level control. This distinction is intentional and reflects the design goals of MQTT as a protocol. Unlike protocols such as OPC, which are traditionally focused on OT-level communication and fine-grained control, MQTT is most commonly used for distributing data to analytics, business intelligence, cloud platforms, and higher-level systems. These characteristics make MQTT particularly well-suited for use cases that are increasingly important today, such as monitoring, data aggregation, and cloud integration, where scalable and decoupled data access is required.